Welcome to the deep dive. Today, we've got a really massive stack of source material from the foundations of generative AI.
Yeah, it's a dense one today.
It really is. But, I mean, it is genuinely groundbreaking. The paper is called World: Soft-Hamiltonian World Models with Selective Memory for Planning.
Right, which sounds like a mouthful.
Totally. But our mission today is to unpack this, because what these researchers are doing is fundamentally shifting AI. They're moving it away from just mere statistical pattern matching.
Exactly. They are giving the AI the ability to truly understand the underlying structural reality of its environment.
Okay, let's unpack this. Because for you listening, think about the last time you were driving in heavy traffic, like trying to merge across 3 lanes.
Always stressful.
Right. You are not just reacting to what is exactly in front of your bumper.
Yeah.
You are actively trying to plan, like 10 steps ahead in this highly chaotic environment.
You're anticipating the speed of a truck way off in the distance.
Yeah, and you're calculating the blind spot of that sedan next to you, and you're even feeling the friction of the road under your tires. Doing that kind of long-term planning without crashing is just, well, it's intuitive for us.
But for an AI, doing that without its imagination completely falling apart is incredibly difficult.
Right, and before we can really understand the solution here, this ham world architecture, we have to understand why current AI imagination just breaks down.
Right, and it really comes down to these systems known as world models.
Like Dreamer v3 or TDM PC2.
Exactly. The whole point of a world model is to let an AI simulate the future in its head before it takes a physical action.
So it's basically saying, if I steer left, the road is going to look like this, and then if I hit the brakes, the car behind me will probably do that.
Right, but the paper points out this massive flaw. As that planning horizon stretches out, like, if the AI tries to look further and further into the future, the simulation becomes wildly unstable.
It starts to hallucinate.
It does. It starts thinking cars can clip through solid walls, or that gravity just, suddenly stopped working.
Which is obviously a huge problem if you're in a self-driving car. So why does it happen?
The authors argue it happens because current models use what they call a monolithic latent representation.
Okay, a monolithic latent representation. What does that actually mean in plain English?
Well, imagine all the different types of information in a physical environment. You've got the spatial configuration of objects, you have the momentum of those objects, and then you have the task semantics.
The task semantics meaning like what the AI is actually trying to achieve.
Right, like reaching a destination or pushing a block. These older models take all those distinct categories of reality and just mash them together into one giant mathematical soup.
So they're just relying purely on statistical correlations rather than any underlying generative structures.
Exactly.
It's like trying to balance your checkbook. But instead of having separate columns for the dates and the dollar amounts and the payee names,
You just mash it all into one number.
yes, you just mush it all mathematically into one single number. Of course, you'd lose track of the math after, like, 3 steps.
Because you have no structure. Without what the authors call structure-aware inductive biases, the AI just can't extrapolate when the physical structure of the world changes.
It just completely loses the plot.
It really does. If an AI compresses the whole world into a single unstructured vector, it doesn't separate the fact that a ball is moving from the fact that the ball is red.
Wow, okay. So since mashing everything together causes all these errors, the logical next step is to, well, separate the information.
And that is exactly what the Hamworld solution does. They split the AI's brain specifically, the planner-facing interface, into very specific, distinct parts.
Right, they decompose this space.
Yeah. They split it into a canonical subspace, which is made up of 2 variables, $5, and then a context subspace, which they call Bayes.
I want to pause on those letters for a second. Because if you know physics, planets aren't just random letters, right?
No, definitely not. In classical Hamiltonian physics, taller represents the configuration, or position, and taller represents momentum.
So color and act as this internal, like, physics engine for the AI.
Exactly. The paper describes them as evolving through an energy-derived vector field. They handle the pure kinematics.
Okay, so that gives the AI a really stable geometric backbone for its multi-step simulation.
Right. But the cider variable, the context subspace that handles all the messy stuff.
Because reality is messy.
Exactly. The taller variable handles the task semantics, the rewards, sudden contacts, and dissipative factors.
But wait, let me push back on this for a second. Strict Hamiltonian physics, that's all about the conservation of energy, right?
It is, yeah.
But the real world has friction. It has air resistance.
Yeah.
If a robot arm hits a table, it loses kinetic energy. So isn't pure physics just way too rigid for an AI planner?
That is a fantastic point, and it's exactly why the authors call it a soft-Hamiltonian design.
Oh, soft. Okay.
Right. A strictly rigid energy field would totally overconstrain the AI. It would lock up the moment it encountered friction. So Ham World uses a mixing parameter.
This is the alpha slider they mentioned.
Yes, alpha. It's a mixing parameter that smoothly blends that strict Hamiltonian vector field with learnable residual control dynamics.
So it's basically saying, hey, follow the laws of physics generally, but allow for some wiggle room.
Exactly. And the Sickewalder context variable absorbs all that non-conservative chaos, like friction.
Okay, that makes sense. So now we have this amazing physics engine in the AI's head. But here's where it gets really interesting to me. What happens when the AI blinks?
Ah.
Because having a perfect physics engine is totally useless if your view is blocked and you don't know the current state of the board, right?
Absolutely. This is the problem of partial observability and action delay on the input side.
A single frame isn't enough.
No, a single frame is almost never enough to form a complete picture. You need what's called a Markov state.
Right, which basically means a complete, self-contained picture of everything you need to predict the next step.
Exactly. If you're missing pieces of the puzzle, you don't have a Markov state.
So how do they cure this AI amnesia?
Enter Mamba.
Mamba.
Specifically, Mamba selective state space memory. Its job is to filter the historical context and feed it directly into those shared latent dynamics.
Okay, so it selectively remembers what it needs. To go back to our driving analogy, if you close your eyes for 2 seconds on the highway, knowing the physics of your own car doesn't help.
Because you don't know where the other cars went.
Exactly. Mamba is the memory that keeps object permanence alive in the AI's mind. It remembers where the cars were, filters out the noise, and feeds that to the physics engine.
It provides the complete input, while the Soft-Hamiltonian structure provides the stable output.
And they ran ablation studies to prove this, right? I mean, what happens if you just completely remove that memory?
It's bad. They call it ablation A2 in the paper. They removed the memory entirely while testing the AI on a robotic task called fingerspin.
Fingerspin. So just a simulated robot finger flicking something.
Basically, yeah. And the return score absolutely plummeted. It dropped from a really strong 254.0 down to a dismal 34.0.
Oh, wow. From 254 down to 34. It just totally failed.
It completely collapsed. They also tested what happens if you swap Mamba for just a standard GRU memory network that was ablation A3.
And how did that go?
It helped a bit, but the multi-step rollout error was still much higher than with Mamba. On the Reacher task, the error was 0.148 with the GRU.
Okay.
But with Mamba, it was only 0.0778. So Mamba basically cut the error in half.
That is wild. So selective state space memory is vastly superior for keeping the physics simulation accurate over time.
Undeniably.
Okay, so we got the theory. We have structured geometry with the Doll and Pyre variables, and we have selective memory with Mamba.
Yeah.
But how did it actually perform when they tried to break it?
They ran it through an absolute gauntlet. The empirical results focus on 4 highly complex deep mind control suite tasks.
Fingerspin, reach your easy, cheetah run, and carpool swing up.
Right. And Ham World just crushed the baselines. Overall, it reached an average AUC of 117.9.
117.9. How does that compare to the older models?
Well, that's a 9.5% improvement over TD-MPC2.
Okay, solid.
And it is a 101.2% improvement over Dreamer v3.
Wait, really? 101%. It literally doubled the performance of Dreamer v3.
It did. And it reduced the multi-step rollout errors to just 45% of TD-MPC2. It cut the errors by more than half.
That is incredible. But the part that really fascinated me was the O tests.
The out-of-distribution tests.
Yeah. The researchers basically threw 12 curveballs at the AI, conditions it had never seen before.
Right. They wanted to see if it would break.
They changed the mass of the objects by 30%. They altered the friction. They added a 2-step action delay.
They even masked 30% of the observation screen.
They just blacked out a third of the screen.
And despite all of that, Ham World achieved the highest return in every single condition. Every one.
So what does this all mean for the user? I mean, why should you, the listener, care that an AI can spin a digital finger even when 30% of its screen is blacked out?
Because it translates directly to real-world reliability.
Right.
When you deploy an AI into the physical world, the environment will shift. Sensors will degrade, motors will wear down, lighting changes.
It's chaotic.
Highly chaotic. Ham World proves that when an AI learns the underlying mechanisms of a system, rather than just memorizing training data, it becomes highly robust to that real-world chaos.
Okay, the performance numbers are obviously incredible. But AI researchers, they are a skeptical bunch.
Very skeptical.
How do they actually prove the AI learned a Hamiltonian energy field? Like,
Hmm.
how do we know it isn't just faking it with some massive statistical cheat sheet?
They anticipated that, so they dedicated a section to Hamiltonian mechanism analysis.
Basically opening up the black box.
Exactly. They used the cheetah run task to visualize the physics it was generating. First, they ran an action-free test.
Action-free, meaning AI wasn't controlling anything.
Right. They injected totally random joint velocities into the digital cheetah, basically giving it a physical push and let it evolve freely without applying new actions.
And what happened?
The learned energy scalar, which they call hot $, drifted by only about 1%.
Wait, so it conserved energy just like real physics?
Exactly like real physics.
That is insane, because they didn't explicitly hard-code the laws of thermodynamics into this AI, did they?
No, they didn't.
So the model essentially derived the concept of energy conservation on its own just to solve the problem.
What's fascinating here is that, yes, the training objective softly guided it, but the AI figured out that organizing its imagination around stable energy fields was simply the most efficient way to plan.
That blows my mind. And what about when it actually applied control?
That was the second test, the action push. When the policy applied control, or did physical work, the energy changed through a process called contour crossing.
Contour crossing, meaning it jumped to a new, higher energy state because work was added to the system.
Precisely. It mathematically understood that effort was applied. And they went even further to prove this, using a UMP visualization.
Right, UMP. That's a way to take the wildly complex AI brain space and map it down to a visual shape we can actually look at, right?
Yes. They wanted to prove that the tall powers and tall variables didn't just collapse back into one giant cloud of data.
Back into the mathematical soup.
Exactly, and the UMP showed they didn't. The visualization proved they formed these distinct elongated manifolds. The physics stayed cleanly separated from the context.
Okay, let's just recap the journey here, because this is massive.
It really is a paradigm shift.
We started with world models hallucinating because they just mushed all their data into one unstructured soup.
Right.
And HamWorld solves this long horizon planning problem by combining two things. First, Mamba memory, which selectively filters the past to fill in the missing details.
Curing the amnesia.
Exactly. And second, a Soft-Hamiltonian geometry, which constrains the AI's imagination to actual, stable, physical rules.
Separating the predictable kinematics from the chaotic reality.
It's just a brilliant solution. It makes you wonder where this goes next.
Well, I actually want to leave you with a final thought to mull over.
Okay, let's hear it.
The source material we unpacked today focuses entirely on physical tasks. Robotic reaching, cheetahs running. Where physics literally means mass and momentum.
Right, literal physical laws.
But what happens when we apply this exact same time in one's tillet to non-physical AI planning?
Non-physical, like what?
Like a world model trying to optimize a global supply chain or a financial market.
Oh, wow.
If an AI can discover the underlying Hamiltonian energy of economics, separating the predictable momentum of markets from the chaotic context of human behavior, how will that change the way we simulate the future of human systems?
That is a staggering thought. Finding the physics of economics. Because, honestly, whether you're an AI navigating global markets or just a human trying to merge in heavy traffic, having a model that truly understands the underlying mechanics of chaos changes absolutely everything.
It really does.
Thank you for joining us on this deep dive. Keep questioning the structures behind the information you consume, and we will catch you next time.